Hey there students, welcome to Psych 53 Lab Module 11, our final module of the semester. Today for this module we're going to be talking about minimum effects testing and Bayesian analyses. So, as you can tell, there's again two different types of subjects, but are actually kind of interrelated with each other. The first thing we're going to talk about is practice identifying minimum effects for rejecting specific hypotheses. So essentially what that means is instead of comparing to just the nil of hypotheses, now we're going to be comparing to different hypotheses. Does this explain like 1% of the variance or 2% of the variance or something like that? And then we're also going to conduct regular and Bayesian ANOVAs to determine whether gender and occupation are related to mental health. So we're going to take our first step into Bayesian analyses in this lesson. So to start off, for part one, what we're going to do is we're going to talk about minimum effects practice. This is where I'm going to say, hey, watch part one of the video, then do part one of the assignment, and then do part two of the assignment as well when after I do talk about part two of the assignment. I'll let you know when that happens. So what is minimum effects testing, or MET for short? So what it is it tests the hypothesis that the effect of a treatment falls somewhere in an interval between 0 and some number. So rather than testing if the effect is precisely 0, we can test if it falls above a range of values, so which is the minimum effect that you're testing. So for example, instead of saying, oh, there's difference of 0, we're saying, is there a difference of 1%, 2%, or something like that is what we'll be doing. So what we're going to be doing for the minimum effects testing is we're going to be using this example. And this example is the authors use right-wing authoritarianism, RWA, to predict differences in response time to in-group and out-group faces and found a squared correlation of 0.07, which, when compared to the nil hypothesis, was significant, with our degrees of freedom is 161 is equal to 4.81. And really, this F values and this significance value are going to come up and be really important here. Okay, so what they did is they found a significant correlation, significant value when compared to the nil hypothesis. But what we're going to be saying is, how does that compare to a hypothesis we're saying it explains 1% of the variance or something like that is what we're doing. And we're going to be doing this in two different ways. The first way is we're going to be using Kevin's minimum effects code that he created for us all. So we're going to identify minimum effects using the effects code. And I'm going to go ahead and log in and open R, and we're going to show you how to do this in R as well. But essentially, what all this is this code where you specify your degrees of freedom hypothesis, which is that 1, your degrees of freedom error, which is the 161, and then your alpha value, which we're going to use an alpha value of 0.05, and the effect that we're testing. And we're going to be testing a minimum effect of 1%. So saying, does it explain 1% of the variance or not? And what happens is we get a value and say, this is the F value you need to obtain in order to be explaining 1% of that minimum effect. So let me go ahead and open up R and show you how we're going to do this. And it's just going to look exactly like this screen, but I'm going to show you how to do it in R. So let's go ahead. Let's open up R. We'll go ahead and create a new project too for this. Let's go ahead and open up R. Let's create a new project, a new directory, new project. Make sure it's saved in that correct place. I'm going to name this Module 11. Let's go ahead and create that project. Okay, and let's go ahead and create a new notebook. And bring this down. Okay, and we're going to go ahead and delete all this. And we're going to be using the same notebook for these things. So we're going to do minimum effects testing and Bayesian analysis. We'll use the same notebook for both sections of this here. And then let's go ahead and create our table of contents. And we'll go ahead and save this. Name this Module 11 notebook. Okay, now that we've gotten that done, what I'm going to do is we're going to go over to Canvas and we're going to go ahead and just copy and paste this code into our R chunks, okay? So let's go ahead and where it is. So you go to your modules and then we go to right here where it says Kevin's R code with underscores all there, .r, and it's going to open up an R script. Now you can work directly within this R script. What I'm going to do is I'm actually just going to go ahead and copy it. So copy. Then I'm going to go ahead and just paste it into a R chunk here. Okay, so what we have here is the same exact code that appears here. Now, there's 4 things that you need to indicate, and the rest of it you keep exactly the same. Is we needed to identify our degrees of freedom hypothesis, which here is 1. So I'll go ahead and see if we can get this all there at one time. So we're going to change our degrees of freedom hypothesis to 1. We're going to change our degrees of freedom error to 161. We're going to keep our alpha value at 0.05, and we're going to change the minimum effects that we're changing to 0.01 for 1%. Minimum effects that we're testing. And then the rest of this, we simply don't change. You keep the SSE the same, the MSE the same, the non-sensor the same, and the QF the same. Okay? And I have an indication here that says where not to change is this place in the red. So if we go ahead and we run this, we get a value of 8.68388. Let me just see if there we go. What we do is compare that to the F value that was obtained. Okay, so in this article, they obtained an F value of 4.81. And what we're saying is it significant for entering in a effect of 0.01 or minimum effect of 1%? And essentially what we're saying is that because we only got an F value of 4.81, it does not fit the minimum effect of 1%. So essentially what you do is you compare the resulting F value needed to test an effect of 1% or more to the obtained F value. In this case, we didn't reach the threshold of F value to have a significant effect at 1%. So the authors needed an F value of 8.68 to obtain a significant effect at the minimum effect of 1%, essentially. And you can change this to anything you want. You can change it to 2%, 3%, 10%, whatever you want. But the higher that this number goes, the more the harder it is going to be, the higher this F value is going to be that you need to obtain it. So authors needed an F value of 8.683 in order to get a significant threshold for a 1% minimum effect. Okay, so that's the first way that we're going to go ahead and look at how to test the minimum effects. Another way we're going to be doing it is through identifying it via Murphy, Myors, and Woloch's 2014 one-stop F table, which is essentially Appendix B of this notebook here. And in the modules, if we go back, we have this Murphy, Myors, and Woloch's Appendix B one-stop F table. I'm going to go ahead and just open it up so that we can see it, but I'm going to be working with the slides. But this essentially looks like this, and what you see is degrees of freedom hypothesis, degrees of freedom error, and then these things that say nil, pow, 1%, pow, pow, 5%, 5%, pow, pow. The nil stands for the nil hypothesis. The POW stands for power, so power of 0.580 or 0.80, and then 1% is a 1% minimum effect. And then we have these other powers, power for 1% and power. So this is power for the nil effect, this is power for the 1%, and this is power for the 5% effect, minimum effect testing. And what we're going to do is we're going to use this table to really answer the same question that we answered before with this minimum effects code that Kevin created for us. So what we do is we identify what our degrees of freedom hypothesis is, which is that 1. Then we identify the degrees of freedom error, and you're going to notice with this one-stop F table, you can't necessarily get the exact degrees of freedom error. As you can see, it goes 90, 100, 120, 150. What we're going to do is we're going to go to the lower, pretty much floor this. So whatever it's closer to at the lower bound. So the closest thing we get is to 150 for our degrees of freedom error. Or more to obtain a minimum effect. So we obtained an F value of 4.81. The first thing we're going to do is say, okay, well, according to this table, is that significant for the nil effect at an alpha value of 0.05? So it's going to be right here. So the way we do that is we go to our degrees of freedom hypothesis, which is 1. And then we go to the closest obtained degrees of freedom error. I usually round down as much as I can because it's a little bit of a safer bet. And we say, okay, did we reach a significant threshold for a nil effect, which is comparing to 0 essentially, at a alpha value of 0.05. So we get that nil, 0.05, and then it's 3.89, which is essentially saying we needed a f value of 3.89 in order to properly have a significant effect for when we're comparing to a nil, saying is the effect 0 essentially. And here, because our obtained f is 4.81, we say yes, we did obtain a significant effect. Correct. Okay, now what we're going to do is say, now can we test for a minimum effect of 1% at an alpha value of 0.05? Did we reach a significant value? And the way that we do that is we simply move down to the 1% here with the alpha value of 0.05. And we say, what was the value we needed to obtain? What was the f value we needed to obtain in order to reach a minimum threshold of 1%? And we needed an 8.61, which you'll see is fairly similar to what we obtained in Kevin's minimum effects code. It's a little different, but it's about the same. But we say we go to the 1% at an alpha value of 0.05, and we say 8.61. So we're saying we need an f value of 8.61 to reach the threshold of a minimum effect of 1% here. And because our obtained f was 4.81, we did not reach the minimum effect. Therefore, we don't have a significant effect with a minimum effect of 1%, essentially, is what we're saying. If you want to do 5%, you can go down to 5%. If you wanted to see what it is to get a power of 0.80 as well, but we're pretty much just teaching you how to do the nil and the 1% at an alpha value of 0.05. Okay, so I'm going to go ahead and pause the video here. Go ahead and see if you can do part 1, which is the minimum effects testing, and then go ahead and continue with the Bayesian analysis next. All right, students, let's go ahead and get started with part 2 of this presentation, which is Bayesian Analyses. So I'm just going to give a quick introduction to Bayesian statistics. I think you got most of what you needed from Kevin's lecture, but I'll just go ahead and just talk a little bit more on it. So to start off, it's becoming increasingly more popular in psychology to do with Bayesian statistics. These models oftentimes are able to account for background knowledge, which we're not really going to discuss in this lab, but it allows us to overcome several limitations of null hypothesis significance testing, or NHST for short, which has contributed to the reproducibility crisis in psychology and reliance on large sample sizes. All common statistical analysis can be conducted in a Bayesian framework. We're going to be learning how to do the ANOVA framework for these Bayesian analysis. So essentially, it's taking a regular ANOVA and turning it into a Bayesian type analysis. So oftentimes with these Bayesian analysis, the interpretations are oftentimes more concrete than a significance test. You're using some clear probability statements associated with it. So today we'll be calculating a statistic called Bayes factor, essentially, which is going to give us evidence for the null hypothesis or evidence for the alternative hypothesis is what we'll be calculating. So these Bayes factors come into these numbers that range from they go from under 1 to above 1, in which 1 indicates that there's no evidence either way for the alternative hypothesis or the null hypothesis, essentially. But what we're going to be focusing on are these Bayes factors here, and this is what we're going to be calculating today, essentially. So what these Bayes factors are is if you get a value of 1, that's saying that there's no evidence either for the alternative hypothesis or the null hypothesis. So a value of 1 is really just an indecisive number. However, once you start getting above 1, then you're starting to have evidence for the alternative hypothesis compared to the null hypothesis. It's saying that we have stronger evidence for the alternative hypothesis. So as you can see, the value of 1 to 3 is anecdotal, of 3 to 10 is substantial, 10 to 30 is strong, 30 to 100 is very strong, and then greater than 100 is considered decisive evidence for the alternative hypothesis. Whereas if we flip that on its head and we start going below 1, then we're starting to see evidence for the null hypothesis, essentially. So there's not this p less than 0.05 thing, anything that we're dealing with now. Now we're dealing with this, how much evidence is there for the alternative versus the null hypothesis, essentially. So anything from a third, so 0.33 to 1, is anecdotal evidence for null hypothesis, or we can have 1/10 to a third, which is substantial evidence for the null hypothesis, strong evidence for the null hypothesis, the lower than it goes, very strong evidence for the null hypothesis, or decisive evidence for the null hypothesis, depending on how low that number goes. And I give you the article that actually features all these if you want to read more on these Bayes factor values as well. But this is just a rule of thumb it gives you here, and we're going to be calculating these today in R. So, a little description of the data set that we're going to be using today. So it's essentially a team of researchers analyzed if people's mental health after retirement was better or worse based on their sex and previous occupation. So we have 3 variables. We have sex, which participant sex, either female or male, and occupation, in which participant occupation was what their occupation was prior to retirement. So whether they're in a professional occupation, a managerial occupation, non-manual occupation, non-manual worker occupation, skilled worker, semi-skilled worker, or an unskilled worker. And then lastly, our outcome variable of interest is going to be a variable called mental, which is essentially the participant's score on a mental health measure. And essentially, higher scores indicate better mental health with that. So let's go ahead. Let's start coding. We're going to go ahead and download the data set first, and we'll put it into our project. And then this is the last coding tutorial of the semester. So let's go ahead and get started here. So the first thing we're going to do is we're going to go ahead and go to our module 11 lab. It's going to be the retirement.csv. So we're going to go ahead and download that. Let's go ahead and open it up. Okay, so as you see, we only have 3 variables. Do File, Save As, Browse. We're going to go ahead and browse it to that desktop. And then Psych63, Module 11, Save. Perfect. Okay, and then we're going to go back to R. Well, actually, we've already got everything here, and I'm going to go ahead and just do hashtag Kevin's minimum effects code, and we're just going to keep working in the same notebook actually. Okay, there we go, and let's go ahead and go to our PowerPoint to see what we have next. If I can remember where that is, there it is. Okay, so I was a little bit ahead, so let's go ahead and download the retirement CSV into the R project file. So we've done that already. So we have three libraries that we're going to be loading today: Tidyverse, Psych, and this new package called Bayes factor. So we're going to have to install the Bayes factor package. So hashtag, and let me go ahead and just load up some notes here real quick. Okay, there we go. Okay, so hashtag load libraries. Okay, and I'm just going to go ahead and bring it up a little bit. There we go. So we're going to do install packages, and it's going to be quotation capital B-A-Y-E-S and capital F-A-C-T-O-R. And we're going to do library, tidyverse, library, psych, and library, Bayes factor. So we go ahead and run all that. Just let it load up. Tidyverse package, psych package, Bayes factor package. Perfect. So I'm going to go ahead and hashtag this out and just get rid of all its output. I'm just going to play it again. There we go. Go ahead and save real quick. All right, let's see what we got next. Okay, so we're going to go ahead and read in the retirement CSV file. So let's go ahead and do hashtag read in data. That, okay, and then we're going to name it retirement. An assignment operator, read underscore CSV. You all know how this goes. retirement.csv. Go ahead and press play. Okay, and just to make sure we have everything right. So we have occupation, sex, and mental, and there's 1,910 observations of 3 different variables. Okay, so we got that done. So let's go and see what we have next. So the next thing we're going to do is we're going to go and factor our variables. I don't think this is completely necessary to do, but it makes it a lot easier. I'm just really into factoring, and it's good to always have practice with factoring as well. So let's go ahead and do this. So, all right, so let's go and do hashtag factor the categorical variables. So we have 2 variables that we're going to be factoring today. It's going to be the sex variable and the occupation variable. So we're going to name this retirement. We're going to go ahead and do it right in there, use an assignment operator, and then we're going to do mutate. So this is going to be the last practice that we all have doing this. This is the last factoring of the semester. Retirement to sex.f equals factor. And then we're going to do sex, comma, then we're going to do levels, make sure that's spelled right, equals C 1, 2, because it's I think it's 1 for female, 2 for male, I believe, comma. And we got labels. And we're going to do equals C quote female, comma, quote male. Okay, we go here, then do comma, then we're going to do occupation.f, create a new variable called occupation.f equals factor occupation, comma, then we're going to do levels equals C. So there are 6 levels to this, so 1, 2, 3, 4, 5, 6, comma, then we do labels equals C. Okay, and then we're going to do quote prof for professional, comma, quote MANAG for managerial, comma, quote non-manual, comma, quote skilled, comma, quote semi-skilled, skilled, comma, quote unskilled. Okay, if I did that correctly, which I think I did, we should have two new variables. There we go. Let me just make sure it's did correctly. Yep, okay, so we got female, male, and then we got all of our occupations there. Okay, so we've gone ahead and done that. We've factored our variables. So the next thing we're going to do, if I can remember where my slideshow is, here it is we're going to go and describe the data set. Okay, so hashtag describe data. Insert in our chunk, so describe retirement, just so we get a good understanding of our variables. So the retirement, so the occupation and sex and sex.f and occupation should be about the same, but our outcome variable of interest is mental, so the mean value is 3.79, and it looks like we have a minimum value of 1 and a maximum of 5, so these scores seem to range from 1 to 5, and the average is 3.79 essentially, with a standard deviation of 0.91. So it seems like they're a little bit more on the higher the better mental health rating, as opposed to the lower mental health. It's a little bit more than half essentially, so that's good to see. Okay, so let's see what we got next. Okay, so we're going to go ahead and just run a normal ANOVA, and then what we're going to be doing is eventually comparing this normal ANOVA to what the Bayes ANOVAs are going to be. So we're going to be running a normal ANOVA, and then later we're going to be running a Bayes ANOVA. So the way that we're going to do that is we will do hashtag run a normal ANOVA, insert an R chunk, And I'm actually going to load this up because it's a little bit different on my R script than it is there. So we're going to do ANOVA LM. We do our outcome variable is mental health, so mental regressed on sex.f, sex.f by occupation.f. And this is just a shortcut that it'll give us if we just do the interaction. It gives us the main effect, which is sex.f by itself, and then the main effect of occupation by itself, and then the interaction between the two as well. Comma, data equals retirement. Okay, so we run that. There we go. Okay, so what are we seeing here? We see that the main effect of sex is not significant, okay? It was 1 degree of freedom, makes sense because there's 2. Occupation at F is significant here, so we're saying that, okay, that there is a significant value with occupation at F. Seems like somewhere that there's a difference in occupation, and then the interaction is not significant between sex.f and occupation.f. So the next thing that we're going to be doing is we're going to be calculating the actual, we're going to be running a Bayes ANOVA, in which we're going to be using Bayesian statistics for these ANOVAs. So we go ahead and run that. Oh, I'm sorry. First, we're going to actually calculate the effect sizes for these. So we're going to get the effect sizes for this. It's always important to get your effect sizes. And remember, the effect sizes is just the SS of the effect divided by the SS of the total. So the SS effect is the sum of squares here. So this is 0.21. And then the total would be all these together. So let's go ahead and do that. So we're going to do hashtag, let's do double hashtag get effect sizes for ANOVA. Okay, and insert an R chunk. So what I think I'm going to do is I'm just going to go ahead and copy and paste these from my notes, but I'm going to just go ahead and explain where these came from. So we can do 0.21 there. So this 0.21 came from here, and then the total is 0.21 plus 1530 essentially. So essentially I kind of rounded these numbers, but 0.21, 0.601 essentially is where I got these numbers from. So this is the effect size for the sex main effect, and then this is the effect size for the occupation main effect. This is the effect size for the interaction between the two main effects, and then we can go ahead and spit out all those as well. So and then we'll do awk PA and then int PA. So if we run all that, we're going to get 3 effect sizes. Oh, see what I did wrong here. Oh, we're actually going to change this to eta. There we go. There we go. So our first effect size for the sexes right here was the equation. Go ahead and get these all evened out. Was 0.00, so it's a very small effect. Whereas the occupation main effect had a larger effect, 0.029, so about 0.03, so a little bit large. So it's still kind of small, but larger than the sex main effect. And then the interaction between the two was small as well. Okay, so we got the effect sizes. So let's see what we get next in our slideshow. So now what we're going to do is we're going to run a Bayes factor ANOVA, and we're actually going to get those Bayes factors from here. And the way you do that is it comes from the Bayes factor package, and we're going to use a function called ANOVA BF. Now we're going to be running this ANOVA in a few different ways. We're going to run the ANOVA BF, then we're going to plot it as well, and we're going to be using this which models equals all to show what each model looks like essentially. So let's go ahead and do that, and I'll explain what all this is after we run it, okay? So here we go. So we are going to do hashtag run Bayes ANOVA. We're going to do hashtag, we're going to do which models equals all, quote, all. Okay, so go ahead, insert a new R chunk. Okay, so we're going to go ahead and create a new object. We're going to name that object M1 from model 1. And we're going to use the ANOVA BF function from the Bayes factor package. Ignore that error, ANOVA BF. Okay, and then it's going to look very similar to how we ran our regular ANOVA factor. So it's mental regressed on sex.f times occupation.f. Occupation.f, comma, data equals retirement, comma, and we're going to use which capital M models equals, and then in quotation marks all. And that's going to just do something where it just gives us all the models possible. Then we're simply going to just output the M1. And the reason we save this into an object is because we're going to use it for plotting it later, actually next. So we go ahead and run that. It takes a little while to load. We're good. Just let it load up. Perfect. Okay, so what do we have here? What it's saying is, in the model, well, actually here, let me go ahead and go to the actual slideshow. So what we're saying here is that so it shows the Bayes factor for all of your possible models, and that's what that which models equals all does. It's saying, okay, these are all the models that I can create from this sex.f and occupation.f. Like I can create a model where it's just sex.f, I can create a model where it's just occupation.f, and then over here are your Bayes factors, and then plus the plus or minus confidence intervals over here too. But as you can see, what we see here is, okay, let's look at first the sex.f. We have value of 0.059. That's a Bayes factor of 0.059. And if you remember, and I'll try and remember where I am, so I'm at slide 24. If we go back to here, evidence for the null hypothesis is when it's below 1, essentially. So that value was below 1, saying that it's evidence for the null hypothesis, saying that there's not a difference between sex. Here we go. So it's saying, hey, there's not that much evidence to say there's a difference between sex. However, with occupation.f, we have a value of 544,17793, a really large value, essentially. And what it's saying is that, hey, there's a difference between occupations here, and there's a lot of evidence for the alternative hypothesis here. So we're not saying p less than 0.05, we're just saying, hey, there's a lot of evidence for the alternative hypothesis here. And then here, what we're saying is just the interaction itself, so not including the main effects, is 0.009. It's saying, yeah, there's evidence for the null hypothesis that the interaction isn't really relevant here. Then, when we have sex.f plus occupation.f, we have a smaller than just the occupation.f evidence itself, but saying, hey, there's a lot of evidence for the alternative hypothesis in this model. And then so on and so on and so on. I can explain all these models, but what you can see, what we're really seeing is that any model that has the inclusion of occupation.f as the main effect result results in an extremely large Bayes factor value, saying that occupation.f seems to be showing the most evidence for the alternative hypothesis. And what we're going to do now is we're going to plot those models and show which ones are showing evidence for the alternative hypothesis and which ones are showing evidence for the null hypothesis. And what it does when we do this plot function on our model is it ranks them. So all you do in order to get that plot, we're going to do hashtag plot models. We simply do insert a new argchunk. We just type in plot and the name of our Bayes factor model, which is M1. I just realized is M1. So we go ahead and press play, and voila. So what we're saying is, as you can see, occupation.f by itself has the most evidence for the alternative hypothesis. With the inclusion of sex, it's still a lot of evidence for the alternative hypothesis, but not as much. And then when you add an occupation.f and then the interaction between the two, it's third ranked and so forth. But overall, occupation.f by itself has the most evidence for the alternative hypothesis. Which is something that you don't get with null hypothesis significance testing. You don't get this idea of like how strong, like it's saying with the p-value is because we just set our p-value to a threshold of 0.05, these Bayes factors just give you more and more evidence whether it's for or against the null hypothesis, essentially, or towards the alternative hypothesis. And that's what the difference is that we're doing here, is that we're saying what is the strength towards the alternative hypothesis. So the next thing we're going to do, if I can get to my slides here, is we're going to change that which models option and to say, hey, what happens when we omit a certain variable from there? So what happens when we omit a variable? What does the Bayes factor variable become? And it's going to show us the top 3 omissions of that. So what we're going to see here, and let's just go ahead and run it. Okay, so we're going to do hashtag. See what I did. And let's do copy. We're going to do which models. We're going to do which models equals top. So we're actually going to go ahead and I'm just going to copy this and do a couple changes to it. There we go. We're going to do M2, and we're going to change this to top. So we just changed this argument to top. So our which models argument to top. We press play and let it load. Takes a little while to load. And there we go. So what we're saying now is when we omit, this shows the biggest change in our Bayes factor score when we omit a certain variable. So when we omit the occupation sex.f variable, so shows how the omission variable will affect the Bayes factor. So as you can see, any model with the occupation .f main effect results in an extremely small Bayes factor, essentially. So when we omit the occupation and sex interaction, it results in a 41.2. But if we just omit the entire occupation.f variable, our Bayes factor is extremely small. So it's saying that when you omit occupation.f, your Bayes factor becomes really small. So this is to the negative 9th power. So this is 0.00000006 essentially is what that's saying. So it's saying that omitting occupation.f, the main effect of it, results in a very small factor. Omitting sex.f still results in a larger Bayes factor, and really, if you omit the interaction between the two, it results in a large Bayes factor as well. So that's what we're doing here. And what we can do next is we can go ahead and plot the M2 and show and to represent it visually. So let's go ahead and do hashtag plot. Let me just do what I wrote here. Plot models. Oops. Okay, and then we do plot M2. So then we go ahead and plot it, and it's saying, look, when you remove the occupation.f main effect, you have a very small Bayes factor. So it's saying, hey, the inclusion of occupation.f is associated with larger Bayes factor scores, or I should say, the omission of occupation.f results in very small Bayes factor scores. Now we're going to go ahead and do the opposite and see what the addition of a variable does. So what we're going to do is do the exact same thing, but we're going to do which models equals bottom now. So I'm just going to go ahead and copy this. I'm going to do hashtag which models equals quote bottom. Do a new hard chunk. And we're just going to change a few things here. We're going to change this to M3. And we're going to change this to bottom. Okay, so when we run this, some time to run. Now it's saying what happens when we include these certain variables. So what happens when we include sex.f by itself? Well, your Bayes factor is 0.059, so it's evidence for the null hypothesis. If you include occupation.f, then you have a lot of evidence for the alternative hypothesis that's at 544.17793. It's a very large Bayes factor value, essentially. So I'm going to go over here. So as can be seen from this model, any addition of occupation.f main effect results in an extremely large Bayes factor, much more than sex.f or the interaction term as well. And then we can go ahead and plot this as well. So we do hashtag, hashtag, hashtag. Let's see what I wrote for this. Plot models. Model. We'll do that. And then we do plot 3. And voila. As you can see, when we add in occupation.f, our Bayes factor becomes very large. Okay, so that really concludes everything for Bayes factors, essentially. I give you a lot of different articles. So one that's about Bayesian statistics and inferences. This one's kind of cool. It quotes Dumbledore, so you know it's probably pretty cool from Harry Potter if you're a Harry Potter nerd. So here's some helpful Bayesian analysis using the Bayes factor package. We really only went over Bayes ANOVAs when there's other Bayes factor ways of getting Bayes factor scores. Here's some great tutorials as well. An example of bottom-up approaches, and so forth and so forth. So I just give you all these resources so you can learn more about Bayesian analysis approaches to statistics as well. And with that, I just wanted to thank everyone for a great semester. Just a reminder, once you're one of my students, you're always one of my students. I'll always be able to, never hesitate to reach out in the future. Here's my personal email address in case I don't have my College State email address anymore. I'll go ahead and keep all my YouTube videos up for future reference. And I just want to say thank you for being such a wonderful class. It's been a pleasure teaching you. I enjoyed every minute or every second of it even. It's been an absolute pleasure. And with that, thank you so much, and looking forward to seeing your final assignments. Thank you so much. Bye.